Welcome to the first lecture for the chapter 7 of class 11 mathematics binomial theorem. So before we get into the concepts of binomial theorem and expansion, let us just look at the basic concept of also why do we need to know the binomial expansion or binomial theorem. What is the significance of utilizing this? So, as we have seen that we have different kind of different identities that we use. Okay, so we know that the expansion of an identity when it is written in this form can be a squared plus 2ab plus b squared. Okay, so we know that this is the expansion of any identity, any kind of a variable that can be written in this form, a plus b the whole square. So suppose when the issue comes when we have to find the power. Okay, so when we have to get the numerical values. Okay, so suppose you are given a number as in 101. Okay, and you have to find the square of it. So while we find the 101, the whole square of 101, since the power, okay, so the indices or the power that is being used over here is small. Okay, so 2, when you have just the squared the number, it is still easy for us to find the answer. Okay, so you can either directly find this, by multiplying 101 into 101. That is, step procedure, and you might even need require calculator to get the value. Okay, otherwise you can also convert it in the form as 101 minus 1 raised to 2. Okay, so suppose you get this you can expand it in the similar form as a square a plus b the whole square. So you will have 100 squared minus 2 into 100 into 1 as 2ab and plus 1 square. Okay, then it's easier to calculate. 100 squared is it's very easy to find if you have any number in the multiple of say 100 or 10, so you can easily calculate the squared or even the other positive integral indices or powers that you can that you are being asked. So this would be 200 and this would be plus 1. So if you calculate it, this is easier to calculate. Okay, so you will get 0.089 plus 1. So this is your value, okay, for this number. Okay, so 101 squared, you can find the value in this way. Suppose you get a larger number. Okay, so suppose you are being asked how to find, oh sorry, this would be plus. I am very sorry for the mistake there. Yes, okay, so over here this would be your 201 and this will be 10201. Okay, so actually this would be your 101 squared. Okay, now suppose you have 999 and you want to find the square of this. Okay, so if you write this again in the form that we have taken before, so this would be 1000 minus 1, okay, and squared. So this would be 1000 squared minus 2 into 1000 into 1 plus 1. Okay, so over here again, as I said, finding the square of any multiple of 10 would be relatively easy. So you can easily convert any such number, in this form, and then you can use the identity. So so if you have a minus b the whole square, so it actually comes down to a square minus 2ab plus b square. So this is what we've already done the expansion of. Okay. So what you get is, so this you can actually, write it in the, this would become a very large, uh, obviously a very large number over here. Then you have 2000 plus 1. If you use calculator, or you easily try to calculate, so you will get this as 9998. Sorry, this would be okay. So you see over here, even when you have a smaller power, and if you have a bigger number that you have to get the power of, either say 2 or cube, it is still comparatively easy. Now, where does the issue arise? Okay, so if you have 98 cube, okay, or you have much more, higher number, so 89 raised to 5, or you have 104 by 6. Okay, so this is where we get, we will encounter problems. Okay, face problems when we try to calculate them. Okay. So hence, when you have identities, okay, now as we know, a plus b the whole square is a square plus 2ab plus b squared. Okay, it's easy to calculate. Similarly, we have already seen that we have another identity with where we have 3. So, and then you have 3 squared b plus 3ab squared plus b cube. Okay, now if you, these two are the very general identities, very no, like very largely used identity. Now if you say you want to find a plus b the whole square, the whole raised to 4. Okay, so now you can convert this easily into any of the smaller power in identities. Okay, so let's take this as a plus b the whole say q and a plus b. Okay, so if we have this, you can simply first expand the first bracket. Okay, so that will be a cube plus 3a squared b plus 3ab squared plus b cube. And you have a plus b. And then if you multiply each term of the second bracket with all the terms of the first bracket, you get a raised to 4 plus 3a cube b. Okay, then plus 3a squared b squared plus ab cube, and then you have a cube b plus 3a squared b squared plus 3ab cube plus b raised to 4. Okay, now if you get all the common terms, okay, and you add them up, so you have 1a cube b, okay, and there is one more here. So a raised to 4 plus 4a cube b, and then you have a squared b squared and a squared b squared here. So again, you have 4a squared b squared, and then you have 1ab cube, and then you have another ab cube here. Okay, sorry, so this is 3, 3, this is actually 6. Yes, so this is 6a squared b squared, 6a squared b squared, and then again you have plus 4ab cube. Okay, and then you have b raised to 4. So you can get it in the identity form, okay, then again you can see that you can expand up to 4 still easily. Now let's take the, we'll try to expand with a larger power. So say a plus b 5. Okay, raised to 5. Now let's see, let's get it in the form of, the identities that we already know. So here expand the first bracket and then also expand the second bracket. So the first bracket is a cube plus 3a squared b plus 3ab squared plus b cube. Okay, and then this will be a squared plus 2ab plus b squared. Okay, and over there now, when you multiply each and every term of the second bracket with all the terms of the individually with all the terms of the first bracket, you will get a raised to 5 plus 1 b a raised to 4 b plus 3a cube b square plus a square b cube plus 2a 4 b plus 6a cube b squared plus 6a square b cube plus 2ab raised to 4 plus a cube b squared plus 3a squared b cube and plus 3a raised to b 4 plus b raised to 5. Okay, now again let's take the common ones. Okay, so you have 3, you first write a raised to 5 over here. Okay, so you have 3a4 a raised to 4b and you have 2 a raised to 4b. Okay, so that will become 5 a raised to 4b. Then you have 3a cube b squared and you have 6a cube b squared and then 1 more a cube b squared. Okay, so over here you have 3 plus 6 plus 1. So that gives you 10 a cube b squared. Okay, and you have the next one you have is a squared b cube. Okay, and you have 6a squared b cube, so that is 7 a squared b cube, and then you have 3a squared b cube. Okay, so this again becomes 10 a squared b cube, and then you have plus a b raised to 4. Okay, so this is 2a b raised to 4, and you have 3a b raised to 4. So that is 5a b raised to 4. And lastly, you have the b5. So you can see using smaller, power and identities, you can get the identities with higher powers also. Okay, a plus b raised to 5. So now, if suppose as we were seeing, so let's try to see. Okay, so suppose the identity for a plus b the whole raised to 4 is a raised to 4 plus 4 a cube b plus 6 a squared b squared plus 4 ab cube plus b raised to 4. Okay, so this is the identity that we know. Now let's see if you have 98 raised to 4. Okay, so let's write it in the terms of say 100 minus 2 raised to 4. So you can directly write it in the form of the expanded identity that we know, or you could simplify it into, okay, or write this as 100 minus 2 squared and 100 minus 2 squared. This would be easy, okay. And since we have already established the identity, so let's just see what we would get if we are using the whole, the whole raised to power. So you have 100 raised to 4 minus 2 sorry. So since we have seen for the plus over here, okay, so maybe we can take an example with plus itself, so it will be easier to understand. So let's take 102. So let's give it the same. Okay, so you have 100 raised to 4, then you have 4 into 100 cube into 2. You have 6 into 100 squared into 2 squared plus 4 into 100 into 2 cube plus 2 raised to 4. Okay, so it's still easier for us to calculate in this form. So you have 100 raised to 4. Okay, so you have 100 and okay, and then you have 4 into 100 cube. So this will be 8 into 100 cube. So you have 6 zeros over here. So over here you have 2 squared. So that is 4. 4 into 6 is 24. So 24. Then you have 4 zeros over here. Then you have 8. So 8 into 4 is 32. 3200 plus you have 8 into 2, 16. Okay. So still it is easier to just add up all of them. Okay. So you will get this as, okay. So you do get the value, okay, that you require, but all the evaluation over here is a lengthy procedure. Okay, so you will need to have you will take some time to compute or evaluate the values that are individual given, but it's still easy because we know the identity that is involved. Okay, so now you can see that when we are actually uh, solving for the identity. Okay, we are trying to get an identity. So anything that has, a plus b raised to n. Okay, so you can see that there is a pattern that is followed. Okay, so its expansion follows a pattern. Okay, so for example, when we have a plus b the whole square. Okay, so you have a squared plus 2ab plus b square. Okay, so there is a you get the numbers, okay, with the exact power of the power that is given over here, but in between you have something that does not have the same powers. Okay, but if you add up the powers that are actually given in this, in the middle term, okay, that is 1 plus 1 2. So if you combine them, this also actually turns out to be 2. Okay, so the total power is also 2 for the middle term. Now, if you see for a plus b the whole cube, okay, so that is a cube plus 3a squared b plus 3ab squared plus b cube. Okay, so the first and the last term have the same power. Okay, so it has the same indices as your, so as the number, or the expression that we are trying to expand. Okay, but in the second term and the third term, if you add up the powers that we are giving the variables, okay, so a squared and b raised to 1, this is again, if you sum it up, it is 3. And similarly, a and b squared, this is 3. Okay, and then let's take a plus b raised to 4, a raised to 4 plus 4a cubed b plus 6a squared b squared plus 4ab cubed plus b raised to 4. Okay. Similarly, you can see over here that the sum of the power, okay, so the sum of the indices that are given in the second term and second, third, and fourth term over here is also actually 4, 4, and 4. Okay, so you can see that there is a pattern that is being followed. Okay, there is a pattern being followed with respect to the, okay, uh, indices. Okay, with respect to the indices for each of the terms of the expansion. Okay, so suppose you want to use this. Okay, so we had got this as a raised to 5 plus 5 a raised to 4b plus 10 a cube b squared plus 10 a squared b cubed plus 5 a b 4 plus b 5. Okay. So similarly, we can see that all the indices of the the terms which are in between the first and the last term, all of them, the sum of these indices is the same as the index that we are trying to expand with. Okay, so this is a pattern that is followed even here. So let's see one example. Okay, so suppose this is where we are using the kind of an addition. Okay, so let's see what we would get if we have a minus b raised to 5. Okay, so that is a minus b to a minus b whole square. So this is a cube minus 3. We'll see what is the pattern that is being followed with respect to the signs too. Okay, this would be plus 3ab squared minus b cube. When you multiply it with the expanded form of a square minus 2ab plus b squared. Okay, so let's see. We have a raised to 5 minus 3 a raised to 4b plus 3a cube b squared minus a squared b cube. And then minus 2a cube a raised to 4b plus 6 a cube b squared minus 6 a squared b cube, and then plus 2 a raised to b raised to 4. And now the last term, so we have plus a cube b squared minus 3 a squared b cube plus 3 a b raised to 4, and we have minus b raised to 5. Okay, So then we'll get the first term as it is. Let's find the similar terms. We have minus 3a raised to 4b and we have minus 2a raised to 4b. Okay, do you have any other terms? No. So this is minus 5a raised to 4b. Okay, and then a cube, a cube b squared. Okay, and then you have 6a cube b squared and you have a cube b squared. So this all of them have the signs as plus. So it is plus 10 a cube b squared. Okay. Then you have a squared b cube, and minus 3. So over here, you can see all of them have the negative sign. So it's minus 10 a cube b squared. Then you have 2ab 4 a b raised to 4 and you have plus 3 a b raised to 4. So now both of them have the plus sign, that is 5 a b raised to 4 and you have minus b raised to 5. So over here you can see that alternate terms have negative sign. Okay, so you can see now if you kind of compare it with a known identity that we know, okay, so that is a cube minus 3 that we've already seen, a squared b plus 3ab squared minus b cube. So whenever you have negative sign, okay, in such identities, when you have to expand them, when you have a negative sign and if you have then every alternate term will have the opposite sign from the one before it. Okay, so you have this is plus, minus, plus, minus, plus, minus. Okay, and similarly over here you can see plus, minus, plus, minus. Okay, so again you can see that a pattern is followed. Okay, pattern followed even in signs. Okay, so now since we know that this is the expansion, okay, so let's uh, try to see what we can get. Okay, so if you have, let's take an easy example and see how we can solve. So you have 98 raised to 5. Okay, so you can write it in the form of 100 minus 2 raised to 5. Okay, now over here we are using such easy examples to see that even if the number is short and even if the form that we write in it is easy to example, how the computation will actually come about. So you have 100 raised to 5. Okay, so since we know that a minus b raised to 5 is actually a raised to 5 minus 5 a raised to 4b plus 5 a cube b squared. No, sorry, this would be 10. And this is 10. Then you have minus 10 a squared b cube plus 5 a b raised to 4 minus b raised to 5. Okay, so this is what we know. So let's see how we can write this. So this is minus 5 into 100 raised to 4 multiplied by 2 plus 10 into 100 cube multiplied by 2 raised to 2 squared. Then is 10 into 100 squared multiplied by 2 cube. Then you have plus 5 into 100 into 2 raised to 4. And the last is minus 2 raised to 5. Okay. So this actually would be 2, 3, 4, 5, 6, 7, 10. Okay, and then you have 5 into 2, so you have 10 multiplied by 100 raised to 4, so that would be 10, 23, 4. Okay, so then you have plus, you have 10 and 4 over here. Okay, so this will be 40 into 100 cube. So 40 into 100 cube would be 1, 2, 10, 10 would be 40. And then this would be 8 into 10. Okay, so 8 into 10, 80. 80 into 100 squared. So 80 into, so 10 is to 4. So 16 multiplied by 32. Okay, so now you can see that, as and when your power, okay, so the index that is increasing. Okay, it's gone now beyond 3, 2, which is easier for us to calculate. This computation becomes very, very difficult. Okay, you can still solve it, but it will take up more time, and it would be, you might end up making quite a few mistakes. So let's just get the answer for it. So actually 103,920,738. Okay, so you can see this is quite high, and you can still compute it. Okay, you can convert it in this form, and addition of such numbers is easier, though time taking, but it's still easier. Okay, so this is the reason why binomial expansion actually came into place. Okay, so binomial theorem, as you will see in the further classes, so there is a kind of a pattern that exists, okay, when we try to expand it. And this pattern can be simplified in a manner which will take very, very less time for us to evaluate the evaluate for higher powers. This also comes in use when we, in physics, when to you have variables that you need to, calculate with respect to a higher power expansion. So then it becomes easy for us to use binomial expansion. Okay, so there is an easier way to expand anything that comes in the form of a plus b raised to n. Okay, so the n is usually a an integer. Okay, so it is an integer. It can be positive or negative. Okay, so first, obviously, we will deal with the positive ones. Okay, so if now let's see what are the few observations that we saw. Okay, so let's take the highest expansion that we have taken. So a plus b raised to 5. So that in turn was a plus 5, 5a raised to 4b is 10 a cubed b squared. Okay. So we have seen that a pattern is followed. So the first pattern that we will try to see is the number of terms in expansion. Okay. So let's see the observations. Okay, so let's call these the observations in expansion. Okay. So the first observation that we will try to see or that we can evaluate from such expansions is the number of terms. So And this is the example that we are taking. Over here, you can see how, let's see how many terms are there. So you have 1, 2, 3, 4, 5, 6. Okay. And over here, your n, the integer over here. Okay. So, the index is 5. So number of terms that we have is 6 when n is equals to 5. So generally, then we can see that, say the number of terms, let's call it uh, C, or maybe, let's see, number of terms, T. Okay, so let's uh, say T is the number of terms. Okay, T is the number of terms, and that is equals to 6 when n is 5. So therefore, we can say that the number of terms, the way they vary for whenever whatever n that we take is actually T is equals to n plus 1 for n power. Okay, so even when you have, for example, you have a plus b the whole squared when you take, okay, example. So n is equals to 2, and when you expand it, you see it's a squared plus 2ab plus b squared, and you can see that therefore t is equals to 3. Okay, so this is one result that the number of terms would be 1 more than the index that we are using. Okay, let's see the second observation. So the second observation that we have is that the powers of A and B. So there is a pattern even when we expand it, and there is a pattern of the powers that are seen in the different terms of the expansion. So in the first one we have a raised to 5. Okay, so and in the next one, let's only consider for a, the powers start varying from, say, 5, and then it becomes, in the second term it is 4, 3, and then slowly you see that it comes down to 1, and the last term, okay, there is 0. Okay, because a raised to 0 would be 1. For b, you can see that the varying or the variation in the powers or the change in the powers is actually in the opposite sense of what we see for A. Okay, so in the first term there is no B, so the power of B in the first term would be okay. So this is the number of terms. Okay, T. Okay, so this is term 1, term 2, term 3, term 4, term 5, term 6. Since n is equals to 5, t is equals to ti. Okay, we will go from to 6. Okay, so let's take this as ti. Okay, so in the term 1, b has a 0 index or 0 power. Then in t2, it is increasing and going up to 1. And then you can see it increases for all the terms up to the last term, where it again becomes n. Okay, and for a, the first term has the same power as the index that we are using. Okay, so a plus b raised to n. So you can see that for a, the change in power is from n to 0. Okay, and the decrease is, it decreases by 1. And for b, the n, the power goes from 0 to n. Okay, increases by 1. Okay, so this is another pattern and another observation that we see in the expansion. Okay, so you should remember this, that for one of the variable, the power will begin from the index itself and go up to 0. And for one of the variable, it will start with 0 and it will go all the way up to the n. Okay, and it increases up to n. Okay, so this can happen for any. So if you take over here a plus b square, so again over here you can see that it starts with n is equals to 2, then it goes a raised to 1 and then 0. And for b, the first term has no b, so that is b raised to 0, then second term b raised to 1, and the last term b raised to 2, which is n again. Okay. So another observation that we see, as I had already partly mentioned it when we were deriving the expansion. Okay, so the sum of the indices of A and B. A and B. Okay, so let's see for A plus B raised to 5. We have A raised to 5. Let's write it as B raised to 0. Okay, since we've already seen that for the if one term starts with n, the power of one term starts with with n, then the power of the other term starts from 0. Okay, so let's take this as 5 a raised to 4b plus 10 a cube b squared plus 10 a squared b cube plus 5 a raised to b4 plus, let's take this a0 and b5. Okay, so again, taking the sum of the indices of AB. So the sum of the indices, okay, sum of indices. This is 5 plus 0. In the second term, again, it's 5, it's 5. Okay, so that should be equal to n. So you can always, cross check when we are expanding if all these observations, these rules are being followed. Okay, so every time, even when we were, expanding over here, whenever we were multiplying, say, a squared with, a cube, you see that the sum actually becomes 5. And for each and every term, even in this, total in detail expansion, you will see that all of these indices, okay, are 5 over here. Okay, so this is 5, this is 5, this is again 5. Okay, so this pattern stays the same. And so, okay, so you can write that sum of indices of A and B for each term of the expansion will be equal to n. Okay, so the actual power, actual index that we are using for the expansion. Okay, so this is the other observation that we see. Now, we saw the patterns that are being followed, the rules like the number of turns of the expansion should be one more than the power that you're using. And the powers of A and B, there is a sequence in which they are, put like one increases from n to, one decreases from n to 0, and the other one increases from 0 to n. And also the sum of the indices of A and B should be equal to the total, the power that is being used for the expansion. Okay, but what is the pattern or the sequence that is being followed by the coefficients? Okay, so over here, since the first and the last one, okay, so for the coefficients. Okay, so this is actually the part in binomial theorem or binomial expansion that we will be focusing on, okay, because it is not easy to always find the pattern or find the sequence with which these coefficients will vary for all the different terms that we are going to get in an expansion. We can easily calculate and get the sequence using the second and the third observation, okay, as well as the first observation. We can very easily find the index, the indices for the A and B term. Okay, but what are the coefficients? So when you have, so this is a coefficient. Okay, so what do you mean by coefficient? Coefficient that comes in front of the variables. Okay, so the C are the coefficients over here. Now, without the coefficient, if you just expand, say if we want to find A plus B raised to 6. Okay, now since n is equals to 6, so number of terms will have to be 7. Okay, so you can just write T1, T2, T3, T4, T5, T6, T7. Okay, so these are the number of terms that we will have. Now we know that, A and B. Okay, so let's just write A, B. These will also, be there in all of the terms. Okay, A, B, A, B, A, B, A, B. Okay, now we know that for the first term, A, okay, so the indices or the index of A in all the terms will first start from the n and go all the way up to 0. Okay, so let's just put the index for A. Okay, so it will start with A raised to 6, then 5, then 4, 3, 2, 1, 0. Okay, and similarly for B, first of all, we know that it will, even if we don't know the rule, okay, or if we, don't consider the rule that it will start from 0 and go all the way up to n, you can easily use the third rule that is present for binomial expansion, that the sum of the indices of A and B should be equal to the n, okay, to the integer or the power that we are using for the expansion. Okay, so 6, so we need to get 6 as the sum of the indices for each of the terms. Okay, so 6, and so this would be 6 plus 0 would be 6, then 5 plus 1 would be 6, 4 plus 2, 3 plus 3, this is 2 plus 4, okay, and then you have 5, and then you have 6. Okay, so it is easy for us to get uh, the variables, okay, for each of the terms. And you can also put in your sign. Now if we have plus, as we said that when it is negative, it is alternately you change the sign. Alternate terms will have negative signs, but now since it's plus, you can easily put the plus sign. Okay, now what would be the issue is, what are these coefficients that will come over here? So coefficient 1, coefficient 2, coefficient 3, coefficient 4, coefficient 5, coefficient 6, and coefficient of the 7th term. Okay, so what would be C1, C2, C3, C4, C5, C6, C7? So this is where, we will face an issue when we are doing binomial expansion. So in the next class, we will see how we will find these coefficients. What is the pattern that is followed by these coefficients of the binomial expansion also. Okay. And we will see that is there an easier way to try to derive these coefficients, and how we can utilize it, or how we can apply it, in real examples that we will see. Okay, so thank you for attending this class, and today we will be ending here. Thank you so much.